Sir, you're muted.
Oh, okay. Sorry, I thought my mic was open. Okay, so we are starting the new chapter, Ionic Equilibria. So to understand the concept of equilibria, first you need to understand the difference between the reversible and the irreversible reaction. So when we talk about irreversible reactions, actually these are those reactions in which product cannot react back into the reactants, and we use only a single arrow which is showing only one direction. So this kind of a arrow is used in chemical equation. Can any one of you give me any example of this kind of reaction? Yes, can anyone give me any example? Okay. Okay, first tell me, am I audible to all of you properly?
Yes, sir.
Yes, sir.
So the most common example is combustions. For example, if you combust methane, it turns into carbon dioxide and water. You cannot make methane again from carbon dioxide and water. Okay. We cannot, make that methane and, oh, sorry, carbon dioxide and water reacts to form oxygen and methane back. So these kind of reactions are irreversible reactions. Next we have reversible reaction. So a reaction in which products formed can react to reform reactants again. And for such reactions, when we are writing the chemical equation, we use this arrow which shows the reaction is heading in both the directions, forward and backward. And can any one of you tell me any example of a reversible reaction? For example, formation of hydrated salt, that it can be turned back into anhydrous by heating. So basically, these reversible reactions are also called equilibrium reactions. And why they are considered as equilibrium reactions? It is because these reactions never goes to completion. Instead, an equilibrium is established between reactants and products. Hence, all of the reactants are not used up. And the yield of product is also less than expected. See, as the equilibrium is established and as all of the reactant is not used up, so it clearly indicates that the product formed is not maximum. The one which we are expecting, it is always lower than this. Is this clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. At the end of the reaction, reaction vessel contains mixture of reactants and products due to equilibrium. So in the container, we don't just get product, we get a mixture of a reactant and products. Is this clear to all of you?
Yes, sir.
Yes, sir.
Okay. So this equilibrium establishes during the course of reaction when the rate of forward reaction becomes equal to the rate of backward reaction. It is also called dynamic equilibrium. Okay, we call it dynamic equilibrium as well. So see, when the forward and the backward rate becomes equal, so there will be no change in the concentrations. No more product will form and no more reactant will used up. So the reaction stops, and that's we call dynamic equilibrium. Is this clear to all of you?
जी सर.
Yes, sir.
Yes, sir.
Yes, sir.
So two of the examples of this dynamic equilibrium you have studied in your O levels. One is the reaction of nitrogen with hydrogen, and iron was used as a catalyst forming ammonia gas. And another was sulfur trioxide gas with oxygen. Sorry, it's sulfur dioxide gas. Sulfur trioxide gas. And third, it's the equilibrium of carbon dioxide gas with the aqueous carbon dioxide. So this one is observed in Haber process. This one is observed in contact process, and this one is observed in soft drinks. Okay, till here, is this clear to all of you?
Yes sir.
Okay. Now we have a characteristic features of an equilibrium reaction. So at equilibrium, or when you say the equilibrium establishes, these characteristic features are observed. Out of these, the first one is it is dynamic. So what it is mean by dynamic? It means that reaction does not stop at equilibrium. Reactant and the reactants and products are continuously changing into each other. So that's why we call it dynamic. Is this point is clear? Now, second characteristic is that rate of forward reaction and backward reaction is same. So it means that by the rate by which the reactants are turning into product in the same by the same rate, product are also turning back into the reactant. Then third, concentration of reactants and products are constant. Some students normally assume constant as same, so it doesn't mean same. Okay. It means now no more reactant is being used up and no more product is being formed. Is this point is clear to all of you?
Yes.
Because
Yes, sir.
as the rate gets same, so whatever the amount of reactants convert into the product, the same amount of product turn back into the reactant again, and we are not going to observe any change And here one important thing to keep in your mind, that it doesn't mean that the concentration of reactants and products are same. That they might be same in very few cases, normally they are not same, but constant.
Sir, so there won't be any heat loss or something like that in those reaction?
Obviously, there must be some heat loss or heat gain also taking place, because if the forward reaction is exothermic, so the backward reaction would be endothermic. And if the forward is endothermic, so the backward reaction would be exothermic. But at equilibrium, we can say there is no net loss or gain in heat, because both heat loss and heat gain would be the same.
Okay, sir.
Okay. Now, equilibrium is only established in closed system. If system is not closed, then any of the reactant or product may escape, and it does not be able to establish the equilibrium. Okay. So if, for example, there is any gas, so that gas can escape, and if it continues to escape, so equilibrium will not establish. Now, equilibrium can be established from either direction. It doesn't mean that we need reactants for a reaction to proceed. If we just use products, so those products can also, start reacting and forming, and forms the reactants. So we can establish the equilibrium by starting from either side. Is this point is clear to all of you?
Yes, sir.
Okay. Have a look over here. Let me explain this. See, this is the reaction. In this reaction, we have a hydrogen and iodine, and they are reacting to form hydrogen iodide. So our reactants are hydrogen and iodine, right? So on here, if you see, we have started the reaction by taking these two in the reaction vessel and allowing to reach the equilibrium. So they will start consuming up, and when 1 mole is left, the equilibrium establishes, because after 1 mole, no more reactants are being used up. Is this understandable? We have took the 5 moles of hydrogen and 5 moles of iodine, and they start reacting, and when their 1 mole are left, the reaction stopped apparently. Is this clear?
Yes, sir.
Yes, sir.
So if you take the
Yes.
ratio, you see the ratio of the reactant and product, it's 1:2. So it means if 1 mole of hydrogen is consumed, then 2 moles of hydrogen iodide will form. So if you see, initially there are 5 moles of hydrogen and iodine, and at equilibrium there are 1 mole of hydrogen and iodine. So how many moles of reactants are consumed? 4 moles each, right? Yes.
Yes.
So if 4 moles are used up, then 8 moles of hydrogen iodide will form, because the ratio is 1:2. So see, 8 moles, when the 8 moles are formed, no more product is formed, and it becomes horizontal, the curve. So see, they both the curves becomes constant at same point. So it is the time where the equilibrium establishes. So here we can see that at equilibrium, there is a 1 mole of the reactant and there are 8 moles of the product. Is this clear?
Yes.
Yes.
And now
Yes,
as
sir.
the time passes, no more reactant is used up, it stays 1, and no more product is formed, it stays 8. Is this clear to all of you? Now, what we did over here, now we take hydrogen iodide, which is our product, in the container and allowed to reach equilibrium, so it decomposes and forming hydrogen and iodine again. So we have started with the 10 moles of this, but what happens after only 2 moles consumed, it doesn't, uh, consume anymore, and it stays constant, its amount stays constant after 8 moles are left. Is this understandable?
Yes, sir.
So if you see, 2 moles are being used up of hydrogen iodide, and the ratio is 2:1. So if 2 moles are used up, then only 1 mole is formed, and after 1 mole of hydrogen and iodine is formed, the equilibrium establishes, and there will be no more formation over here as well. So see, here we have started with hydrogen and iodine, and at equilibrium we got 1 mole of hydrogen and 1 mole of iodine and 8 moles of hydrogen iodide, right? But when we started the reaction with hydrogen iodide, so see, only 8 moles of when the equilibrium establishes, again 8 moles of hydrogen iodide are there, and 1 mole of hydrogen and iodine are formed, and there will be no change. So see, if you use the same temperature conditions, then the ratio of the reactants and product always remains same. It doesn't matter whether you started the reaction from the reactants or you started the reaction from the products. Is this clear to all of you?
Yes.
Yes.
Yes, sir.
Anyone
Yes, sir.
of you has any confusion, please ask. Okay, then just complete the graphs quickly. So we can start, remember this thing, we can start the equilibrium reaction from either side. Yes, is everybody done with the graph? Yes, is everybody done with the graph?
Yes, sir.
Okay. Now we are going to do Lee-Chatterjee's principle. It will help us to understand that on shifting the conditions where the equilibrium position will shift and whether we are going to get the greater amount, larger amount of the product or lesser amount of the product. So we are going to discuss Lee-Chatterjee principle. So remember, Lee-Chatterjee's principle states that equilibrium shifts in a direction to minimize the change which disturbed the equilibrium by changing any factor. So if the equilibrium is established and any one of the factor is, changed, and due to that change, now there is no more equilibrium. So the position of the equilibrium shifts in a direction which actually minimizes that change, and as a result, equilibrium is restored again. Is this understandable to all of you?
Yes, sir.
So
Yes, sir.
seminar asks you to write that, define the term Lee-Chatterjee principle, and then they ask you by providing a condition, and you have to predict the condition and then explain how the equilibrium will change if due to that condition. So the first factor is concentration. So if the equilibrium is established, then it means that the reactants and products are in the equilibrium to each other and they stay in the same ratio, isn't it? So think if at that moment what we do, we added more reactant in it. So obviously that ratio between the reactant and product is disturbed. Now there is our excess reactant in it. So to reestablish the equilibrium, where the position of the equilibrium would shift towards right or towards left, towards reactant side or towards product side?
Product.
Product side, obviously, because there are now more reactants that we have added some more amount of reactant in it to minimize the, to minimize this change or to remove the excess reactant. Equilibrium shifts in a right, and as a result more product will form, and it will happen until the equilibrium is restored again. Is this understandable to all of you?
Yes, sir.
Yes.
Yes, if any one of you has any confusion in this, please ask.
No, sir.
Okay. Okay. So I'm just noting down the key points over here. That reactants. Okay, let me do one thing. At equilibrium, see, because the equilibrium is established. So what we did, we increased the amount of the reactants. So there are now more reactants in the mixture. To remove that excess amount of the reactant, equilibrium shifts to right until the equilibrium restored again, and there will be more amount of the product. Is this understandable to all of you?
Yes, sir.
Okay.
Yes, sir.
If the equilibrium is established and we have removed some of the reactant from the equilibrium mixture, so what will happen? Then there is a lesser amount, the amount of the reactant is decreased. So to overcome that decrease in the amount of reactants, equilibrium shifts to the left, and the products turn back into the reactants again until the equilibrium is restored, and due to this the amount of the product will be lower. Is this clear to all of you?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, so you have to explain the answer in that way. Okay, so if we increase the product, there are now more product in the mixture. So to decrease the excess product, equilibrium shifts to the left, and the products react back to form reactants again until the equilibrium is restored. So the amount of product will be lower. Is this clear?
Yes.
If we remove some of the product from the equilibrium mixture, so there would be, the amount would be lesser, the change. So the equilibrium shifts towards right to decrease the change in the amount of the product, and as a result more product will come until the equilibrium establishes again. So I have made the summary over here. Equilibrium shifts to right in this case. Is this clear to all of you?
Yes, sir.
Yes, sir.
Okay. Now after concentration, we has a next factor, pressure. Do remember that this is for those reactions in which there is a gas. Okay. And there is a rule for a pressure that you have to keep in mind. Increase in pressure shifts the equilibrium. Yes, can anyone tell me where the equilibrium would shift?
Right.
Yes, Ahmed, Amna, anyone else? If we increase the pressure, where the equilibrium would shift?
Sir, towards right.
No, there is no right or left like the concentration, okay? Here you have to see towards where less number of moles of gas are present. Whether it's a product side, if the product side has lesser number of moles of gases, then the equilibrium would shift towards right by increasing pressure. If the reactant side has a lesser number of moles of gases, then on increasing the pressure, equilibrium would shift towards left. Is this understandable?
Yes, sir.
So it means that decrease in pressure shifts the equilibrium towards where there are more number of moles of gases are present. So it means if pressure is increased and equilibrium shifts to right. How could we know that equilibrium shifts to right? That the product yield increases, right? So there are two possibilities. Either this will happen, or if we increase the pressure and as a result, we can observe that equilibrium shifts to left. So if the equilibrium shifts to right, it means there would be less moles of gas at product side. And if the equilibrium shifts to right, shifts to left on increasing pressure, then it means less moles of gas at reactant side. Is this clear to all of you?
Yes, sir.
Okay.
Yes, sir.
If we lower the pressure, then in which direction equilibrium will shift? Towards where there are more moles of gas. So there are again both the possibilities that equilibrium either shifts to right, or if we lower the pressure and as a result equilibrium shifts to left. So it is because more moles of gas at product side. That's why equilibrium would have shifted towards the right on lowering the pressure. And in this case, it means that there are more moles of gas at reactant side. That's why on lowering the pressure, equilibrium will shift towards the left. Is this clear to all of you?
Yes, sir.
Yes, sir.
If anyone of you has any confusion, please ask. Okay. Then after this, we have a next factor. That is temperature. And we will discuss this temperature in our next class, okay? From temperature onward, we will continue in our next class. If any one of you has any confusion till here, please ask. Yes, still here, is this clear to all of you?
Yes, sir.
Okay.
Yes, sir.
So I'm ending the class over here, and in the next class, we will continue from here, okay? Okay, take care, everyone. Allah Hafiz.
Officer.
Allah Hafiz.